I'll talk a bit about, that was all about the design process. I'll talk a bit about the detailed physical modelling we've done for the geotextile structures. I'll go through a few examples of how we arrived at the design curves. The basis of our program was the 0.75 cubic metre containers, which was what was generally used for open coast usage at the time that we did this model testing, but the model testing has probably pushed it up to the bigger units as the default for the open coast. The detailed modelling we did, we used a length scale of 1 in 10 because we had to get, we needed them to fail within the limits of the wave flumes we've got. Now wave flumes can make waves of around about 1/2 metre. So we can make 1/2 metre waves in our flumes, and obviously we need the structures to be able to fail to get the design curves. What we found, when we did the initial calculations, we thought we'd get away with a 1 in 4 scale based on some of the previous studies that have been done for these units. So we thought we could test them at a 1/4 scale, but we basically couldn't fail them at a 1/4 scale. We built something, put the biggest waves we could, couldn't fail them. So we kept changing the scale. We went to a 1 in 5, 1 in 6, right out to 1 in 8, until we finally settled on 1 in 10 because we needed to be able to fail them. If you're technically involved, it's called Freudian similitude, the main basis of the testing, but if you don't do model testing or if you're not a coastal engineer, you can ignore that one. We also, because by simply changing the scale, so the 2.5 cubic metre units scale as a 1 in 13 to what we did in the model. So we can simply scale up the results to simulate the 2.5 cubic metre units as well. Some of the things that we scaled, it's not as simple as just putting a length scale. We seriously considered all the dimensions of the containers, plus the volume, the density, the shape of the containers relative to real world ones, the hydraulic conductivity of the fabric itself, and then the sand we use to fill it in the model. We have to try and scale that. And also the fabric to fabric friction to try and make the friction between the units in the model match or scale up to be equivalent to the friction between the units in the real world. So here's some examples of the physical model testing. We started some very basic tests because before we could do the whole thing, we had to be able to fail them. So this was done at a 1 in 4 scale, and you can see they look pretty big, chunky units. We put waves on those in the flume at 1 in 4 scale, and the biggest waves we could get, we couldn't move them. So that changed our 1 in 4 scale, so we had to shift from 4, and we went from 4, 5, 6, 7, 8 until we could reliably fail them in the flume. So initially we did some preliminary tests just using monochromatic waves, which are just completely regular waves that look like a boat wake, just a set distance between them because it's very quick to test like that. And we looked at single layer and a little bit of difference with double layer as well to see the relativity between those. And to make sure, we really did 19 separate tests just to make sure we could fail them and look at the difference between single and double layer, set the model scale. We then shifted to phase 2 of the testing where we did around about 50 tests like this. Our wave flume for these tests is about 3 metres wide, but again, these are fairly preliminary tests, so we just narrowed the flume to 1 metre in this case, so we didn't have to invest a lot of effort in rebuilding the structure because we were still at the early stage of testing for this. So we ran it at 1 metre wide flume, ran a whole lot of different things. We initially started at 1 in 8 scale at this, and then before we went to the full scale testing, we changed it to 10 scale because we still couldn't reliably fail the bags in this circumstance. And this is what it looks like in the flume with waves running up over the structure, potentially causing damage. So we analysed the results from that phase 2 of the testing, and we did 60 different tests, but instead of monochromatic, we used what's called irregular waves, which is like the real ocean. So you get big waves and small waves and groups of waves and calms in between them. So the irregular waves, using what's called a John swap spectrum, simulate real world conditions a bit more. We did 60 different tests like that. And the data looks to be a bit scattered, but we used what's called the Dowley-Dean and Dalrymple surf-so model to bring the waves down to what they are at the structure. Once we did that, we got very nicely fit design curves for them. And we plotted the design wave height as a function of the wave period at the structure. We adopted this 0 to 2% initial damage as our design criteria. And that gave us, so we really worked out where we were going. We moved into phase 3 of the testing, which was around about, you can do the numbers, probably 75 separate tests. We tried to look at all the permutations you can have without obviously testing for 10 years. We still only had limited resources. So we tested in our 3 metre wide wave flume. We did it full width, non-overtopped. We looked at 3 different structure slopes because most of these structures are built at a 1 to 1.5 slope, which is around about 30 degrees. But we also looked at a 45 degree slope, 1 in 1, and a flatter slope, 1 in 2 slope. We looked at single and double layer structures, always in a stretcher bond, like a brick wall where each course is overlapping the course below it. The bags were always oriented with the long axis of the bag pointing along the shore. There are some schools of thought that the bags could be pointed out to sea and it may have different stability, but the way that they're traditionally built is the bags aligned along the shoreline, so parallel to the dune. So that's how we tested them. We ran irregular waves, around about 1,000 irregular waves using what's called a John swap wave spectrum. We also looked at foreshore slopes. Now this is just the upper beach slope. It's not, once you go offshore the beach flattens out, but the near shore slope between the structure and the normal waterline, we use slopes of 1 in 5, 1 in 10 and 1 in 20. We always put the toe of the structure at -1 AHD, 1 in 10 scale. The wave height at the structure we use, we varied at the significant wave height between 0.5 metre and 2 metres, wave periods 5, 10, 15 seconds, and the still water level at the structure, we varied it from 0.5 metre, from 0 AHD, 1.5 and 3 metres AHD. If you're right into water levels, you'll know the open coast water levels on Australian east coast, that's about your 1 in 100 year level, 1.5 metres AHD, but realise we're inside the surf zone, so we have waves set up on top of that. So this is a wave setup level inside the surf zone, and that pretty much represents about the highest wave setup level you'll get inside the surf zone anywhere on the east coast of Australia. You could theoretically get a 10 metre wave, which would give you 1.5 metres wave setup on top of your 1.5 metre water level. So that's 3 metre AHD water levels, pretty much an upper limit for anywhere open coast, east coast Australia. Wave run up still goes above that as well. So this is the detailed phase 3 testing, which was where the design curves got developed. So a bit of a run through about what's involved doing a test like that. Before we did this work, we actually went out and measured some real world structures that were built and got some detailed measurements on the construction dimensions, the as-built dimensions of the bags, and we actually got load cells on cranes and measured the dry density, the dry mass and the wet mass and the submerged mass, and worked out a whole lot of densities and fill ratios as well. Translated all those into the model scale, and we carefully filled these up to a known mass. Every one of them was weighed to a known mass, sealed up, and there's an example of a finished bag. We then built our sand slope in the flume, put a layer of geotextile under it, as is recommended in the real world, and started building these structures up the geotextile slope, similar to how you build a revetment in the real world. And Ian here is still with us despite building, probably laying, I don't know, 100,000 geotextile bags over the course of this project. He's remained with us. Didn't send him insane. So here he's constructing a geotextile structure up the slope, a 2-layer structure. And this is what the finished product looks like in the flume. This is the beach in front of the structure, and we varied the slope on that, as I said, from 1 in 5 to 1 in 10 to 1 in 20. But as you move out into deeper water, traditionally east coast Australia, you've got about a 1 in 50 slope once you start going out into the deeper part of the surf zone. But the upper part of the beach is much flatter than that, is steeper than that. So that's what it looks like in the flume. The early tests, we did some monochromatic. This is just a bit of a comment about using single versus double layer bags. The early tests, we constructed monochromatic waves and we didn't repair them, but we found that with the single layer structures, the failure progressed quite rapidly. So you get a few bags displaced and then the entire slope would just slide down and fail. So there was quite rapid progression to failure. We did the same thing with double layer bags. So we repeated a whole lot of tests. We repeated about 15 tests or 10 tests with double layer bags. And if we used a 0 AHD water level, we couldn't fail the structure. So we went from single to double and we couldn't fail it at low water levels because the waves just weren't big enough hitting it. When it did fail in double layer, it's a very slow, gradual failure, and generally it's only the outer layer that fails. The inner layer still stays intact. So through in reality doing about 150 separate tests, this is what the test data looks like. I'm not going to go through all of it, obviously. Everyone will go to sleep showing 150 test results. This is how we came up with our damage criteria. So for a given condition, we do the test with different wave heights at the structure. And there is a key to that, but this particular one is a 1 in 1.5 slope, 5-second waves. So 5-second wave period. This is the amount of damage for each test. So running 1,000 waves, so we sit there, run 1,000 waves on the structure, see how many units have been dislodged. It's 0 for all these different significant wave heights here. So even up to, so between, our early test, we start with 0.5 metre waves, no damage at all. We crank it up to about 1.3 metres for this case, no damage at all. So there's been 0 units dislodged. Once we get, in this particular case, 1.5 metres. So you can see these are all individual tests, these data points. We go above 1.5 metres, we start getting around about 2% of containers dislodged. Physical modelling is still, it's not an exact science, it's still not 100% repeatable. You know, we can find a case here where that withstood 1.7 metre waves, but generally you see once we go above 1.5 metre waves, we've started getting damage, so 4 or 5% damage in these cases. So for the design curves, we set that as our initial damage threshold there. You can see there's definitely no damage there. Generally there's damage above that threshold. So that's a 5-second wave. Just bear that in mind, the damage occurs about 1.5 metre wave height. We shift to a 10-second wave, so these are higher energy waves. The damage threshold drops to around about 1.3 metres. You can see very little damage, maybe 1% damage here, usually about 4 or 5% here. We shift to 15-second waves. These are high energy ocean swell waves, much more power in the waves. The threshold for no damage drops to about 1.2 metres. So in some circumstances we're getting quite high damage, 15%, which is failure of the structure once we get up here. So we set the design curves to this no damage threshold always. This is just a slightly different, this was similar to the last example, but if we change the slope to 1 in 2, so we've got a 1 in 2 slope, so a flatter slope. Interestingly, if you're used to designing rock structures, you'll think, oh, 1 in 2, the structure will be more stable. It goes a bit converse to that with geotextile structures. So our threshold wave height at the structure is actually lower for a 1 in 2 slope. And at first we were a bit perplexed by that, but there is an explanation which I'll get to. So this is a repeat of the earlier design curves I showed, but for different structure slopes. So again, our wave periods along the bottom, 5 seconds out to 15 seconds. This is the wave height that can hit the structure before the units will be dislodged. The one in the middle is the standard recommended 1 to 1.5 slope, the diamonds here. And for 10-second waves, it's about a 1.3 metre wave can hit the structure. If we shift to a steeper slope, a 45-degree 1 in 1 slope, that rises up to 1.5 metres. If we drop it to a 1 in 2 slope, so go a bit flatter, it reduces to around about 1.1 metres. So in summary, the design wave height decreases for longer wave periods. So as you get longer wave period, a smaller wave will dislodge the units. It also increases for steeper revetment slopes. So as we go steeper, we can withstand bigger waves, which is a little bit counterintuitive. If you're used to designing rock structures, that's not necessarily right, but because of the interlocking and the way that gravity acts on them, they lock together more as you go steeper, but that introduces other problems. We're not the only ones who found that. We were a bit perplexed at first. Probably the only other reasonably detailed study on these through the world was done by a fellow called Juan Recio in Germany. Now he did a PhD on this, and in some ways he did a PhD, so it was one person working for 3 years on this problem, and effectively at WRL we had 3 people working for 1 year on the same problem. So we probably did about a similar amount of work, but we did it in a third of the time than he did, and we were a bit more practically focused, whereas his work was quite academic, as you'll see. So he developed some stability equations as well from his PhD. Some fairly complicated equations though. It's German practice is to only fill the containers to 80%. So his bags were only filled 80%. Australian practice has been to basically shove as much sand as you can into those bags so that they're filled to 100% capacity. They're filled as tight as they can be. When you only have the 80% filled bags, they get a bit floppy. So that when waves hit them, they tend to flop around a bit more because they're not as constrained by the tensile force of the geotextile. His work clearly showed that the geotextile fill ratio is a critical stability parameter. So he did acknowledge that, but he did all his tests at 80% fill rather than 100% fill. So that's one of the reasons probably for the difference in his numbers. And the most difficult part, as I said, is you need to use the still water the velocity at the still water level to drive the stability equations. We did do a comparison of the numbers that we got versus Recio's numbers. It's a whole lot of numbers, I won't go through them, but his supervisor was Hossein Umarachi, who's a fairly prominent coastal engineer in Germany, and he published another paper from the PhD, came up with we basically used his equations, came up with some numbers, used our own study to come up with what sort of numbers we're getting. I'll just focus on this middle section, the 1 to 1.5 metre slope, 1 to 1.5 slope structures, which is the recommended one. They got quite similar numbers at low wave periods. So 5-second wave periods, they're getting about 1.6 metre wave can be withstood by the structure. We're getting 1.5. So we're getting very similar numbers at short wave periods. If you go to a 10-second wave period, 1 metre versus we're getting 1.3, you go to a 15-second wave period, about 0.8 of a metre wave, whereas we're getting 1.1 metres. So we're getting better stability at long wave periods. We believe it's because their containers aren't filled properly. They're sort of, with the long wave periods, high energy waves, they're just kind of flopping around, and they tend to flop around and dislodge a bit easier. So high wave periods, their criteria is lower wave heights, and simply because the fill ratio is, as far as we can tell now. That said, we only tested a single fill ratio, which is 100%. They only tested a single fill ratio, which is 80%. But we believe that's the reason for the differences. So basically, their numbers generally underpredict what we came up with, and the reason is the fill ratio. They indicated it is quite a critical parameter. You can speak to one of us. If you do want the references for these, they're just listed down here. There was a 2003 paper at Coperdek and another 2008 paper at Coperdek, plus Ressio's PhD is out there. You can find that on the internet, even if you're really inclined to look at 200 pages of equations about water velocity or whatever. A little bit of talk about groins. So I've finished on revetments for the moment. A little bit of a talk about alternative. The other primary use of geotextile container structures is for groins. So not far from here, Maroochydore up on the Sunshine Coast is an example. Here's another groin being constructed in South Africa. Warren has some words about this, but you can see the most interesting thing is the way they're constructing this groin, and they're driving the tracked excavator out onto the structure. So obviously that's invoking a lot of stress upon these units, but anyway, this is another. There's been quite a few groins built around the world. This is an interesting way of building them. We did some very brief testing on groins, but I would say that on revetments we've done comprehensive detailed testing. Groins we've done very preliminary, very brief testing, but nevertheless we've got some numbers which something is better than nothing, but we certainly haven't solved all the problems with groins. The testing that we did, we used a 1 in 13 scale on the 2.5 cubic metre containers. I've got a picture of what it looks like, but we used 4-unit high structure built in a pyramid. We put the crest at +1 metres AHD, which is typical of what you might use for a groin for a short to medium life, just a temporary groin. We tried, part of the reason for this, there was a question, are you better to point the bags out to sea for the groin, or are you better to put the bags across the groin? And some of that's dependent on how you want to build it as well. We used 3 water levels, a 0, a 1 and a 1.5 metre AHD water level. Also realising groins are going out into the surf zone, so the full wave setup doesn't happen until you're at the shore. So once your groin is out inside the surf zone, you're not getting as much wave setup as well. So that's probably that's still a reasonably high water level once you're out into the surf zone. For this limited testing, all we did was have the waves hitting the groin at 30 degrees. So instead of coming square on, which we'd call 0, they were a 30-degree angle. So indicative of fairly more of a wind swell situation, or not a really long period swell, but nevertheless 30-degree wave angle. All we did was use 100 regular waves. So we just did monochromatic waves, 100 of them until we failed it. And we just used a wave period of 10 seconds, which is pretty typical for what you'd use on East Coast Australia for something that's not intended to live for a long time. This is what it looked like, the 2 different setups. So this is what they look like in the flume without water in it. So this is our groin structure coming out from the shore, and we run waves through like this. This example, the bags are across the structure. This is just further down. So the bags are going across the structure, so the bags are aligned this way across the groin. We also looked at them with the bags pointing out to sea. So the long axis of the bags here is coming off the shore. This is a lower example of it. So the bags are pointing out to sea here. So that was part of the impetus for this testing, was which is potentially a better way to build the groins. I'll give you the answer on that towards the end, but I'll show you a few other interesting findings. So we tested it just with monochromatic waves. We basically just kept ramping the wave height up until we failed, or until we damaged it, and then we used what height actually damaged the structure. So we didn't run 1,000 irregular waves and look at what happened. We just kept ramping it up. So this is when we had a 0 metre AHD water level. So this is basically mid-tide level, remembering that the crest of the structure is 1 metre AHD. So the structure is about 1 metre out of the water, which may give a different type of damage or failure than if the structure is submerged. So what happened? The number we found about a 1.6 metre wave actually damaged the structure. So we actually would just run 10 waves, stop it and see whether it damaged. And then we got to 1.6 metres, and this is what happened. Realising this structure is 1 metre out of the water, so these levels here, so this is the head of the groin, so it basically just parted under the water a little bit. So this is the damage that occurred. The head of the structure, these units parted themselves out, this layer parted out, the crest actually stayed intact. So that was the damage mechanism that we saw. These started trying to walk their way off the groin and fall off the groin. So that was how, with a 0 metre AHD water level, that was how it failed. We rebuilt it, ramped it up to a 1 metre AHD water level. So that's basically just a pretty big high tide, about a once a fortnight high tide on most of the east coast at the peak of the tide. The structure crest is 1 metre AHD, so the water level is basically completely level with the top of the structure without waves there. So it's getting a little bit submerged too. So everyone here's probably swum at the beach sometime. If you can get yourself under the waves, you don't get as much damage as if they hit you full on. So that's potentially a different damage mechanism. So what we found, interestingly enough, same thing, about the same wave height though, about a 1.6 metre wave is still what caused the damage here. Very similar to the last one. We then ramped the wave height, the water level up to 1.5 metre AHD. So we've actually got deeper water potentially, and so the structures are now quite submerged. So remembering the crest of the structure is at 1 metre AHD, so now the structure, so this is really a storm event. The structure is now half a metre under the water. And we'll see what happened there. You can actually see what happened. Once the structure's under the water, it was actually the crest bags that were damaged. So the earlier test you saw the bottom of the structure started to pull out, but now the bottom of the structure is so far submerged that the waves are going over the top of that. It's like diving under a wave. It's not really doing anything. It's the crest bag that was damaged. So the damage started occurring to the crest. So you can see this bag here originally belonged there. So that was the only damage we had at the really high water levels, was the crest ones started peeling off. If you've ever been up to the Maroochydore groins up here, not far north of here, you see similar damage mechanisms to what we've seen here. In some circumstances, these bags are taken out, but at the really big high, after the really big storms, it's the crest bags that get taken off. So what we also found was that for the cases we studied, whether you put the bags pointing out to sea or along the shore for the groins didn't make any difference at all. We couldn't find a difference for the cases studied. And probably the reason is that because we used a 30-degree wave angle, the area of the bag that sees the wave is about the same, regardless which way you orient it. So that's probably the reason. So if we actually look at the area of the bag, the blue line is the long axis along the shore. The purple is the bag pointing out to sea. If we look at the area of the bag that sees the wave, it varies depending on which angle the waves come from. So because we tested 30 degrees, these lines are not very different. They're kind of similar, and certainly once you go here, they're identical. So that's what we surmised is the reason, because it's reasonably intuitive that if the bag's pointing its long axis into the wave crest, you'll probably get less damage. But once you've got 30 degrees, it's almost a bit equal which way it's coming. So that's probably the theory, but we only did one range of tests. So there's certainly a lot more work to be done in that area. So from that limited test, what we found is that we could find no preferable orientation based on 30-degree wave attack. However, theoretically, it probably is better to point the bags out to sea. And that uses less bags, and it's theoretically more stable. So we don't have any objection to doing that, and it's a more economical way of building. Further testing, we should be looking at different angles. So we should be looking at 0, 15 and 45 degrees as well as the 30 degrees that we did to really get any real handle on that and any real handle on the data points. So that's the end of my talk on groins. Just onto some overall conclusions about this talk. We did an extensive physical modelling program examining the stability of sand-filled geotextile containers and revetments. The dimensions of the actual units were based on real-world field measurements, and what we did was probably about the most extensive program that's been done in the world so far. For the ElcoMax product, we'd recommend a 1 and 1.5 slope as the best overall compromise. The 1 and 1 slopes are actually more stable, but they start to have usability and public safety issues, and it's quite hard to build a sand slope of that, to build the sand at that slope to put the structure against. So from a constructability point of view, 1 to 1.5 is the recommended slope, unless you have a very good reason to deviate from that. We've published some design guidelines based on this output. It's been put in the last two Australasian Coasts and Ports, or the last Australasian Coasts and Ports conference as a paper that summarises all these design conditions for real world conditions. We tried to come up with quite practical guidelines where we simply put a wave height at the structure and wave period as the main things to think about, rather than some fairly esoteric inputs such as water velocity at the still water level. So that's the end of my talk. Thanks for your interest. Any questions or discussion we can have after the talk. Thanks.